Okay, good morning. Welcome back, everyone. A few things that we want to do today. If you look at our course schedule, I'm going to talk very briefly about the escalator solution, the escalator problem we worked on the other day. I collected your painting problems and your banana peel problems, so I'll look at those later today, hopefully. And then we are looking at sections 2.4 and 2.5, and I'll intro that in a little bit here. So the first thing I want to talk about is the escalator solution. And I'm just going to walk you through the way I did this. Now, again, I've said this before. Just because I do it one way doesn't necessarily mean that you have to do it that same way, right? There's lots of different ways to think about this. What I hope you're coming up with here is this ability to keep your thoughts organized, to keep your variables organized, to make sense of the problem and persevere in solving it, check your solution, make sure it works, that kind of stuff. So when I approached this guy, I thought of it as distance equals rate times time. Some of you didn't even do that, which is fine. Some of you were like counting the railing marks or trying to count the steps, or you were doing a whole different kind of approach, which is fine. But I thought of this as a distance and a rate and a time. So we know that our friend Dan, sometimes he was just on the steps alone. There was no escalator at all. Sometimes he was going with the escalator, and then at the end he was going against the escalator, right? So I thought each one of those has a distance, rate, and a time. So the distance, his rate alone times his time alone. The distance when he was with the escalator, with help, is the rate with and the time with. And then when he was against it, there's a rate against and a time against. And I know some of those rates and times, and I don't know some of the other rates and times. Like the only ones that they gave us was when he was by himself, it took 12.7 seconds. And when he was having the escalator help him, it took 8.9 seconds. And we just got that from the video. And you just had to use your eyeballs to try to find that white flicker on the timer, right? So I can solve then. If I say the distance is just one flight of stairs, I can solve for his rate alone. So when he's all by himself, just on the stairs, he can do one flight of stairs every 12.7 seconds, or 12.7 seconds of a flight of stairs per second, if we think of it that way. And his rate width, obviously, it's faster, right? 1 divided by 8.9 is a larger number than 1 divided by 12.7. It's a faster rate when he was there. When he was going against, we don't know that rate. In fact, we don't know that time. The time is what we're trying to solve for in the very end, right? The time against, that was our final solution, or our final thing that we're trying to find. Well, when he's going against the escalator, if we know how fast he can do it alone, and if we know how fast the escalator is, I could subtract those two, but I don't even know how fast the escalator is yet, right? So I got to figure out what is the rate of the escalator. Well, with my two pieces of information that I know that the rate of the escalator, it's going to be whatever his rate was with the escalator minus what he can do alone. The difference would be the amount that the escalator helped. So I said his rate with was this, his rate alone was this. If I subtract those two fractions, that'll give me the rate of the escalator. So if I go back up here, the rate of the escalator is subtracting those two fractions. The rate alone, I already knew that one. So I got a fraction minus parentheses, fraction minus parentheses. This whole mess right here, this just says, please pull out a calculator, is what that tells me, right? Like that would be awful to try to do that by hand. So I pull out a calculator and I get this big ugly decimal. What does that ugly decimal represent? It is the rate that he's going to move when he's going against the escalator. And now I can solve for time against by doing that. And I got 22.16 seconds. And what did the video reveal? It was close to 22, wasn't it? Wasn't it 21 or 22? It was close, okay? I got pretty close. So well, first of all, did I get it right? No. theoretically, I got this problem wrong, because did it take him exactly 22.16 seconds? No. Okay, so let me lecture at you for a little bit. Forever and ever and ever, math students have been improperly taught that in math, your answer is either right or it's wrong. Does anybody ever feel that way? You do a math example, blah, 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 and it's either right or it's wrong. Now, I can tell you that on the painting problem and the banana problem, there is one exact solution for both of those. It's either right or it's wrong. Why do those problems have an exact solution, whereas this problem doesn't necessarily have an exact solution? Can anybody explain that to me? Go ahead, Harmony.
Because we were left to assume what we were looking for in the video rather than if we're given the problem with actual numbers and variables.
Yeah, like I said, it took 12.7 seconds when he was doing it on the stairs. But Colby might have watched that video and said it took 12.8. Okay? Well, which one is it? Is it 12.7 or is it 12.8? I don't know. We're relying on our eyeballs and there's all kinds of measurement error going on here, right? And what does it even mean to get to the top? Is it when you get your first foot to the top? Or are we talking when we get both feet to the top? Do you see all that? Did Dan get tired halfway through and slow down? Or did he keep the pace going? I don't know, right? There's all these things going on. Were all these sources of error present in the banana problem? No. The banana problem just basically gave you the information you needed and you had to do the computation. And yes, there is one correct answer for that. Okay, let's say Karen and Jamie are painting a garage. Do you think if we actually took a video of Karen and Jamie painting the garage and did it similar to the escalator problem, that there might be a lot of sources of error? Somebody might stop and take a break. Somebody might paint faster, then they might paint slower. There's a lot of things going on. Did I give you those sources of error in the problem that I presented? No. I just said Karen can paint it this fast and Jamie can paint. Do you see how those are really simplistic and contrived problems, whereas this is kind of more of a real life thing going on? So what I'm trying to say is just because I did not get the right answer doesn't mean I did anything mathematically wrong, right? Like, I would argue that this is a pretty mathematically sound argument. I could make an argument, construct a viable argument, and pitch it to somebody else with confidence. And some of you also made a really good argument and could pitch it to somebody else with confidence. Okay? So, comments or questions on that? We feel okay? Okay. I'm interested to see what you came up with for your banana and your painting, but I'll give those back to you hopefully on Wednesday. So what I want to do here today is I want to move on. Notice that section 2.3 was on models and applications. Okay? The next three sections we're going to do are going to be solving equations. Okay? So when we're solving equations and I just give you the equation and I say solve for the equation, there's going to be a correct answer. Right? Okay. So here we go. Here's what we've done so far. If you kind of go back, we've been working on solving equations basically this whole time, except for some of our application stuff we did in 2.3. We worked on linear equations. Hopefully you can solve linear equations. Okay? You should get plenty of practice doing that from section 2.2 on your quiz and whatnot. In linear equations, I said there's nothing special about x. A lot of times it's just gathering like terms. Sometimes we use the distributive property. Linear equations largely are 8th grade stuff. You should be able to handle that, I would think, quite easily. The rational equations were definitely tougher. What's the difference between a linear and a rational equation? This is where we got the x down in the denominator and we had to work with fractions. Definitely tougher. Okay? But can we still solve them? Of course we can. We talked about using the lowest common multiple and multiplying both sides so the denominators go away. You get plenty of practice on that, also in your 2.2 quiz. And then I put out the watch out for division by 0. Remember, anytime we divide by 0, that does not exist. So there are certain answers that we definitely cannot have when we have rational equations. So what we're going to work on now is going to be a review. You guys have all done quadratic equations. You did them in Algebra 1, and then you did them again in Algebra 2, and then if you took a senior level or advanced math or an Algebra 3 or pre-calc or something like that in high school, you did them again. We're going to go through them rather quickly, just by way of review. So, how do you recognize a quadratic equation? You see one walking down the road. How do you recognize it?
AX squared plus BX.
Yeah. Yeah, it's an x squared. There's an x squared in there, raised to the second power, right? So, really quick, see if you can do these in your head. I'll give you about 15 seconds. Go. Just scratch it out on a piece of paper. These are quadratic equations. Solve for x. Anybody got the first one? Say again, Colby? Nope. 3. I heard a 3. Does anybody agree with that?
3 and -3.
Thank you. There's 2 answers to every quadratic equation, right? There's actually 2 numbers that work for this. The answer is 3 and -3. They both work because if I put in 3 for x, 3 squared is 9. That's a true statement. But -3 squared is also 9, right? -3 times -3 is positive 9. So 2 answers for that guy. How about the second one? Plus and minus 4. Again, 2 answers. 4 works, -4 works. Okay? How about the third one? I heard a 5i. Anybody else? -5i? This one does have 2 answers again. Was anybody tempted to say 5 and -5? Does 5 work? No, because 5 squared is 25, and we're trying to get to -25. Does -5 work? No, because -5 times -5 is positive 25, and we're trying to get to -25. So some of you already know where I'm going with this. Some of you are like, how can a number times itself equal a negative number? Because we learned a long time ago that a positive times a positive is a positive. And a negative times a negative is a positive. So how in the world can I take 2 numbers, multiply them together, and get a negative if they're the same number? It can't work unless we introduce this idea of imaginary numbers, right? So those of you who know what you're doing here, the answers are 5i and -5i. But we have to understand what I is in order to even understand that, right? Let's come back to this I thing in a second here. What happens if I gave you this equation and I asked you to solve for x? Notice I'm giving you the equation and I'm giving you the graph. Some of you might be able to look at the graph and you can see the answer without even doing any algebraic work on the equation. Can you see it? You should be able to see it. What are my answers? 3, positive 3, and -2. It's saying, where does this equation equal 0? Where does it equal 0? Well, it equals 0 when it hits the x-axis. That's where y is equal to 0. So at positive 3 and -2. So if you have the benefit of the graph, you can see that. If you were just doing it on paper and pencil and you didn't have the graph, what strategy might you try? Unfoil, the opposite of foil, right? Foil is the distributive property. What's the opposite of distributing it out? We call it factoring, right? So you might see that this guy, this is a trinomial that factors into 2 binomials, and then we apply our zero product theorem, and we can say, if I wanted to make this parentheses equal to 0, I would put in a -2. And if I wanted to make this parentheses equal to 0, I'd put in a positive 3. Therefore, my 2 answers are -2 and positive 3. Again, 9th grade stuff. But we're going to get a little bit of practice reviewing this. Okay? Let me shoot you another one. Just looking at the graph, what do you think it is? 2? Why does this one only have one answer? And I just said a minute ago, all quadratic equations have two answers. This one is what we call a double root. The only answer is 2. You guys agree? 2 is the only number that works. And you can see that if you choose to factor it. If you factor it, you find out that both your factors are exactly the same. They're both x minus 2. Therefore, 2, again, it's an answer twice. It's a double root. So what's our answer? 2 works. Okay, I'm going to give you one more. Just looking at the graph, where does this guy equal 0? Obviously, it doesn't. So it never equals 0. It doesn't go low enough, right? So if you start to solve this guy by hand, what are you going to find out? What do you think? Say again? There's going to be 2 answers. But what are my answers going to end up looking like? Are they going to be real numbers? No, because we can see clearly with our eyes that there are no real numbers x's that cause this guy to be 0. Therefore, my 2 answers are going to be imaginary. They're going to involve I, right? So that's where the question mark comes in. There is no real solution to this equation. There are only imaginary solutions. So let's talk a little bit about imaginary numbers. I am not going to spend a lot of time in this class on imaginary numbers. You guys have probably heard of it. I got a couple slides here, definitions. Imaginary numbers, why do we even need them, right? Well, there's all kinds of applications of imaginary numbers that we are not going to do in this class, okay? Anybody who does electrical engineering will tell you that using complex numbers, a plus bi in the imaginary plane, makes things very, very simple that would be very difficult for electrical circuits and flow rates and stuff that is way over my head. I'm not an electrical engineer, okay? But I know that it has very practical uses, telecommunications, cell phones, polarized sunglasses. There's all kinds of uses for imaginary numbers. Why are we going to use imaginary numbers? In Math 107, we're not going to do any of the stuff that you saw in the previous slide. We just want to be able to understand and express the solution of a quadratic equation that doesn't have any real solutions. That's all we're doing here. Okay? So again, we're just solving equations and we want to be able to express our answer. So we're not going to spend a ton of time on this. The definition of I bet you guys already knew this. I is the square root of -1. It's just a shorthand way to write the square root of -1. So what happens if I square both sides of that equation? If I square the left and square the right, then I squared would be equal to -1. So by definition, that's really all you need to know about I. I is the square root of -1, or I squared is equal to -1. And if you know that, you can do adding, subtracting, multiplying, and dividing with imaginary numbers. And we're not going to do a lot of this in class, but you are going to get a chance to practice a lot of that on your 2.4 quiz, on the online quiz that I gave you. So I is the square root of -1. And any complex number, a complex number is a number that has both a real part and the imaginary part. So the real part, A, plus the imaginary part, BI. There's always an I in there. Okay? So we can add, subtract, multiply, and divide complex numbers. Again, you're going to get a chance to practice some of that in your 2.4 quiz. And if you look through the textbook, remember when you click on that 2.4 quiz, there's always those little 6-7 minute videos that you can watch if you want to refresh your brain on a little bit of that. The only thing I'm going to point out here in class is that second bullet. When we divide complex numbers in the form a plus bi, it is useful to multiply the numerator and the denominator by the conjugate of the denominator. What's the conjugate? You guys probably have seen this before. Maybe you didn't remember it. If we have an imaginary or complex number in the form a plus bi, then his conjugate is a minus bi. You just change the sign. So if it's 2 plus 7i, his conjugate is 2 minus 7i. If it's 3 minus 2i, his conjugate is 3 plus 2i. Okay? The beauty of multiplying a complex number times his conjugate is that if you multiply it out, all the imaginaries go away, and you're left with a real number. Okay? Every single time, if I take any complex number, multiply it times his conjugate, all the i's go away and I'm left with a real number. So an example of that would be just this example. Let's say I wanted to take 5 plus 3i, which is a complex number, and divide it by 2 minus 4i. Okay, all we're doing is arithmetic here, a division problem. A good strategy, take that original fraction. I'm going to multiply both the top and the bottom by his conjugate. Now I can do that. That's perfectly legal. I can take that guy times that, because if my numerator and denominator are exactly the same, anytime I have a fraction where the numerator and the denominator are exactly the same, that fraction is just equal to 1, right? And if I take something times 1, I'm not actually changing it. Do you guys agree? So all I'm doing is taking this guy times 1. So notice what happens. I got to do top times top. I got to multiply that. I would use the distributive property, or like Harmony said earlier, some of you have heard of FOIL. F-O-I-L, first, outside, inside, last. That's just a mnemonic device to remember how to use the distributive property. That's all it is, right? So I would use the distributive property on the top. I would do the same thing on the bottom, but notice what happens to my bottom. I'd get 2 times 2 is 4. I do the outside, 2 plus 4i, I get 8i. I do the inside, 2 times negative 4i, I get minus 8i. The 8i and the negative 8i cancel, they go away, all my i's are gone. So I'm only left with a real number on the bottom. I clean it all up, I do the arithmetic, and I have my final quotient right there. So again, this isn't rocket science. What did we do? We took 2 imaginary numbers, we divided them. Big whoop, right? Okay, it's just a little bit of algebraic manipulation and algebraic procedure. That's all I'm going to talk about with the complex numbers. Again, you'll get a little bit of practice with that when you do your quizzes. Let's actually solve some quadratic equations. Okay? Here's a couple other ones for you to solve. Notice the header says solve by using the square root property. What is the square root property? It means we're going to take the square root of both sides of the equation so that we can change an x squared into an x. Because the square root, if I have an x squared and I take the square root of that x squared, I'm now down to x. And that's what I'm trying to do, right? I'm trying to solve for x. So, see if you can solve all 3 of these guys. Now you might need to do a little bit of other algebra first before you decide to take the square root of both sides of the equation. So keep that in mind. And I'll give you a minute and then we'll go over the solutions to all 3 of them. Just a friendly reminder that you're actually going to get 2 solutions for each one of these, right? You should. Finish all 3? Yeah? Give you another minute. Okay, I'm going to show you how I would have done these. You can follow along, see if you got the same thing. I look at this guy here, and the first thing I'm thinking is I'm going to divide both sides by 3 because I want to get that x squared all by himself. So now I know that x squared is equal to 9. And I can take the square root of both sides to change my x squared into an x. Every time I take the square root of both sides, I know that there's both a plus and a minus. So my answer is x equals plus or minus 3. There's 2 answers to that guy, right? 3 and negative 3. I hope you were successful on that one. Okay? What's a good thing to do to this second one here? Yeah, let's get rid of the 1 first. So what happens if I called it 5x squared equals 50? That helps, right? What else is a good move here? Divide by 5. I'm trying to get that x squared by himself, or isolate him, if we want to use mathematical terms. So now I got x squared is equal to 10. Now what should I do? Square root both sides and I'm home free. So square root, square root. Remember, I'm going to have plus or minus. So x is going to equal plus or minus. Square root of 10 is just some ugly decimal, so I'm just going to leave it as the square root of 10 and call it good. Right? How about the last one? What's a good strategy here? I could distribute it out and square it, so I'd take x plus 2 times x plus 2. I'd get x squared plus 4x plus 4. I could do that, but I think I would be going backwards because I've already got the whole darn thing squared, and I'm trying to solve for x, right? So a better thing to do would be square root both sides. The square root is going to cancel with the square, right? So the square root cancels with the square. Do you guys agree? Because they're inverse operations of each other. Of course, I got to square root the other side as well. So now I got x plus 2 is equal to plus or minus 5, because the square root of 25 is 5. And now I just got to move the 2 to the other side, subtract 2. So x equals negative 2 plus or minus 5. And I can do the arithmetic on that, right? Negative 2 plus 5 gives me 3. And negative 2 minus 5 gives me negative 7. So my 2 answers are 3 and negative 7 are my 2 answers. I could plug it back in and see if it works, right? So that's examples of how to use the square root property. The square root property is typically pretty easy to use. The only problem is not all the quadratic equations that we want to tackle are in the form that allows us to use the square root property, right? So again, you're going to get lots of practice on this. I know we're going through this kind of fast. Some of this, I know for you guys, is like, oh my gosh, this is college pre-calculus? This is 9th grade. Come on. Okay, and if you feel really confident, that's fantastic. But I know this is good review for some of you too who are like, wow, I haven't done this since 9th grade, right? So that's why we're going over it, but rather quickly. So I can't do the square root property on these because these are now in that form that Martin rattled off earlier, ax squared plus bx plus c, right? There's trinomial. So I can't just take the square root of both sides. So if you look at the directions there, it says solve by factoring. And if we can factor it into 2 binomials, if I can make a binomial times a binomial equal to 0, then I can set each parentheses equal to 0 and I can solve. So some of you can probably do this really fast. Can you guys factor this first guy in your head? X minus 5 and x plus 2. Do you guys agree with that? So what did Hannah do there? She unfoiled it. She undistributed property it, right? She went backwards. Now, if we were to distribute back what she just rattled off at us, or if we were to FOIL it, would we get back to the original? Yes, we would. That's a skill. being able to take that trinomial and factor it into two binomials. And how do you get good at that skill? You start to recognize patterns and you practice. And I'm going to show you all kinds of practice that you guys can get for doing that. But let's say we get good at doing that, like Hannah is obviously good at doing that. Okay, she could do that mentally. Once we get to that point, it should now be easy to solve this guy for x. Anytime I take any number times another number and that's equal to 0, what do I know about my two numbers? There's only one way to multiply two numbers to get 0. One of the numbers must be what? 0. It has to be. If I take two numbers times each other, one of the numbers has to be 0 if I want my answer to be 0. Could both of the numbers be 0? Yeah, because 0 times 0 is 0. Does it matter which of the two numbers is 0? No, I'm going to get 0. So I need to look into the possibility that the first number is 0, and I need to look into the possibility that the second number is 0. I need to tackle both, right? What number would make my first guy 0? 5. What number would make my second guy 0? -2. There's my two answers. 5 and -2, right? That's what we call the zero product principle. Can you guys factor this one? A little bit tougher. What do you think? We want factors of 36 that add up to -13. What times what gives me 36 such that if I add the two I get -13? Yeah, -4 and -9. Do you guys agree? Again, that's a skill. That takes practice to look for and make use of structure. I can see patterns. Martin saw the pattern, right? It's x minus 9 is one of mine, and x minus 4 is my other one. If I FOIL that out, I'd get x squared minus 4x minus 9x, which gives me minus 13x plus 36, and it works, right? Heavy lifting's done now. What are my two answers? 9 and 4. 9 and 4. Exactly. Okay. There's another example. X squared minus 3x minus 10. Can I factor that guy? Yes, I can. I factor it. -2 and 5. That's the one that we just did, right? What about the one on the bottom? Solve by factoring. It's not factorable. You ask yourself, what are the factors of -13 that add up to 4? Well, the only factors I can think of for -13 is 1 and -13, or -1 and +13. Do either one of those add up to 4? So we're screwed, and we cross this one out on our homework and we move on? Maybe? If I can't factor it, this is where it gets a little more complicated, right? Factoring typically is easy if you can figure out how to factor it. Taking the square root property, typically pretty easy, just square root both sides. When we get to these, it's a little bit more complicated, right? So some of you already know where we're going with this. There's this procedure that we can simplify this known as completing the square. Heard of it? Anybody heard of it? Anybody know how to do it? Nobody? We want to make a square. Okay? We want to make a square. What do we know about a square? All four sides are the same length, right? So the height, I'll call this the height of the square and the width of the square. Do you guys agree that h and w would be exactly the same if we made a square? So our goal is to make a square. Let me erase that. Okay, let's take each one of these guys. Let's just look at the x squared. If I made a square and I said it has a width of x and a height of x, do you guys agree that that's a perfect square? And if I want to know the area of a square, I take the height times the width, and that gives me the area of the square. So what's the area of that square? X squared. So we're going to do this geometrically. X squared is a perfect square. X times x. That's really, really easy, right? But I'm not done. I don't just have x squared. I still have that 4x and I still have that minus 13 hanging out, right? I'm done with the x squared. I've geometrically represented him. Let's look at the 4x. How could I geometrically represent 4 x's? Some of you maybe have seen this before. I'm going to make a little bar here, and I'm going to give him a width of 1. And I'm going to make another one, and I'm going to give him a width of 1. What's the height of those two rectangles? You can see I already have it written down way on the left. What's the height? It's x, right? So do you guys agree that a width of 1 times the height of x would give me an area of x? Because 1 times x is x. And this one would also be x. Well, that's only 2 x's. How many do I need? I need 4. And I'll show you why I'm going to do this, but I'm going to put the other 2 on the bottom. Right here and right here. And I'm going to call that a 1 and a 1. What's the width of those two? X and x. So do you guys agree that this one is x and this one is x for area? So what do I have on my screen so far? I have an x squared and I have a 4x. Do I have a square? Of course not. That's like some goofy looking hexagon right now. It's not a square. What am I trying to do? This procedure, it has a name. I'm trying to what the square? Complete the square. Right now it's not a square. I'm trying to complete it. So in order to complete it, I need to fill in, see if I can get fancy here. I need to fill in the remainder of the square. There's a chunk missing down here. Do you guys see the missing chunk? Do you guys know what the area of the missing chunk is? There's an area to that guy. Can you see it? How wide is it and how tall is it? It's the width is 2. Do you see the 1 and the 1? 1 plus 1 equals 2, right? So this width is 2. How tall is it? It's 2. Jamie made it look like a rectangle with his bad drawing, but what shape is it? It's a square because this is also 2 as well, right? So this is a 2 by 2 square down here, right? And a 2 by 2 square has an area of what? 4. So is that the number that I currently have up in my equation? No, I have a negative 13. Does negative 13 make a perfect square? No. What number does make a perfect square? 4. So there's a procedure here. I don't want negative 13. Bad. Bad number. That's not the number I want in that position. What number do I really wish was in that position? I want a 4 in there. Can I just swap out the negative 13 for a 4? I can do a little bit of algebraic magic to make it work, right? So let's say I take my original, x squared plus 4x minus 13 equals 0. Let's say I move the 13 to the other side by adding it to both sides. Is that legal? Sure I can. Just add 13 to both sides of the equation. What number do I wish I wanted in here? 4. If I write in a 4, I can only do that if I do what? I got to add it to the other side as well, because you guys learned way back in the 8th grade algebra, whatever you do to the left-hand side, you got to do to the right-hand side. So I just added 4 to my left-hand side, so I also need to add 4 to my right-hand side. Am I legal so far? Yes. All I've done is I've moved the 13 to the other side. I've added 4 to both sides. Now I can factor. And by looking at my picture, I can already see what my factors are going to be. I got the height, which is right there, of my square, and I've got the width, which is right there. And it happens to be a square, therefore both parentheses are the same. What are they? X plus 2, I can see that. X plus 2 is my width. X plus 2 is my height. So this is x plus 2 and x plus 2. And what's left over here? 17. And now I can rewrite this guy. Instead of writing both parentheses twice, I can write it like this. That's what it means to have 2 of them. And now I'm back to a problem that I can solve using my square root property like we did about 7-8 minutes ago, right? Square root both sides. X plus 2 is equal to plus or minus root 17. So x equals negative 2 plus or minus root 17. There's my 2 answers. That was kind of a long, tedious process, but I wanted to show you. Has anybody ever seen that before? Complete the square. What does that mean? We don't have a square, but I want to make it a square, so I do some algebraic magic to make it happen. That's what I was trying to demonstrate. Okay? You're going to get lots of practice on doing this. So, I'm going to discard that. I want you to go to Blackboard. And I'm going to show you a couple things underneath course docs and links. Under course docs and links, if you scroll down to section 2.4, 2.5, turn this off. 2.4, 2.5 at the bottom. Okay, the PowerPoint that I just showed you is right there. Factoring practice. Lots of factoring practice. You do not have to do this if you don't want to. I put a PowerPoint on here to help you get better at your factoring skills. What are you supposed to do? You take, these are just 10, see how I can grab them and move them? Like that's a 0. It's a tile. And I'm going to place each tile in a box. So I got 10 of them. I'm just randomly placing them. You need to place them. These are all wrong, by the way, because I'm not even looking at the right one. You need to place them appropriately so that all 10 go into all 10 boxes. So we're practicing factoring. And then you can notice down in the bottom it says page 52. You can go down to the solutions. And right here is the solutions for page 52. And page 53 and page 54. This is just practice. Okay? So you go ahead and practice with that if you want. You don't have to. Nothing to turn in. The other thing that you can do with practicing, I put 2 links down here. One of them is factoring quadratics. One of my favorite math websites is mathisfun.com. It is so, it gives you really good information and really good practice without cluttering it with really heavy notation. Okay? So if you want to practice factoring, here is a great link to just scroll through and look at a few examples. And then at the bottom, they give you a little practice quiz. And it says factor. And you can just choose which one it is. Again, I'm not requiring you to do this at all. This is purely for your practice. Okay? What I am going to require you to do is that second link, and we're going to do it in class right now. It's called completing the square. As far as I'm concerned, in my experience of 16 years of teaching math, the completing the square part is the part that stumps students more than other parts of solving quadratic equations. Therefore, we're going to spend a little bit more time on this. So what I'd like you to do is just kind of scroll through. Hey, look at that. See that picture? Just like the one Jamie drew, except much prettier and nicer on here. Right? Showing you geometrically what it means to complete the square. So I want you to scroll through this, and you can read this as fast or as slow as you want. Okay? And then I want you to take the quiz at the bottom. Okay? And when you're done with the quiz, I want you to take a snapshot of that quiz, just like you did with that GeoGebra tutorial. Take a snapshot of your finished quiz and place that snapshot in your shared folder so I can see it. I want to verify that you did it. And what grade am I going to give you? I think it's worth 5 points. I got to double check. I'm going to give you whatever grade that you get on this quiz. So if you don't like your grade on this quiz, you best do it again before you take the snapshot of it. Does that make sense? So when you get down to the bottom, you're going to have a question 1, blah, blah, blah. You're going to do an answer. So let's say I put D. Whoops, I got it wrong. Next question. Oh, I got that one right. I didn't even read the question. Next question, blah, blah, blah. I'm going to keep clicking on these. See how many I get right, how many I get wrong. Hey, I got that one right. What number am I on here? I'm on number 8. Quiz results. This is what I want a picture of. I would go to my snip tool, which I use on my PC. I would go like this. I would save that picture with my name on it, put it in my Algebra 2, Chapter Algebra 2 folder, in my shared folder, so that Jamie can give me a grade on it. If I actually got 3 out of 10, I'd probably redo it before I submitted that for a grade, because that's not very good. So if you don't like that, get out of it, do it again. I don't want to do that one. I'm exiting out. I'm going back and I'm doing this quiz again. Any questions? Yes.
I thought 5 when we get 3 out of 5 if we got the guy.
No, you get 1.5. Good question, though. Okay, so again, I want you to scroll through and read the content of the page before you do the quiz. Now, if you're a completing the square expert and you know what you're doing and this has all been, childish review for you, then you go right ahead and you work on that quiz. But if you want to go through some of the content of that page, I suggest you do that first. You got 4 minutes left of class. You can work on it right now. The only other thing that I'm giving you for an assignment, notice the assignment here. It says take a snapshot of the completing the square Mathopolis quiz. That's what I was just talking about. Put it in your shared folder. By the way, I told you guys, I thought I told you guys, but maybe I haven't. You should have a folder that says Algebra 2. We're on chapter Algebra 2. And then we're going to start on the other book, chapter 1, chapter 2. I want your folder organized by subfolders because eventually there's going to be a lot of documents in there, and I don't want this laundry list of all these, and then it's really hard for me to find the document that I'm looking for. And only you can organize the folder. I suppose theoretically I could do it since you shared it with me, but I don't want to work that hard. So I want you to organize your shared folder by subfolders, by chapter. So it's easier for me to find what I'm looking for. And then the 2.4 and 2.5 quizzes, the online quizzes on Blackboard that I want you to take. You should already be working on the 2.1, 2.2. I think they're called assignments, not quizzes. They use the word assignment, right? If you haven't done any of those yet, you are way behind, okay? So you should be keeping pace with the sections that we're working on. Okay, so you can sit and work on this now if you want for the next 3 minutes. If you want to take off early, you can take off early. I'll walk around and help answer any questions that you have. Otherwise, we'll see you on Wednesday.